Okay, so let's get started. Today we will go through the physical layer, continue our journey there. So it will be physical layer today, 2 lectures, and wrapping up tomorrow afternoon. And then we will be done with the physical layer and then start moving up the stack again. Okay, so a little bit of a review. So last time we talked quite a lot about this pulse amplitude modulation, which is the workhorse of most physical layers. And the idea is to convert bits to signals. And this is done, so we have bits to the left and we have signals to the right. And we do that by converting the bits first to symbols. And then each symbol is multiplied with a pulse to form a pulse train, which is this pulse amplitude modulated signal. The mapper here is basically a lookup table that takes input bit patterns and outputs an amplitude. These amplitudes are collected in this set curly A. And each time we have a block of bits, we get out a symbol, and then we multiply that with a pulse. And we do that every capital T seconds. So again, we have bits, we have symbols, we have a symbol alphabet. These are the possible output amplitudes. We have a pulse shape G. We have the time between consecutive pulses. And since T is the time between consecutive pulses, the symbol rate, the number of symbols that we transmit per second, is just 1 over T. While the bit rate we have here is how many bits we transmit per symbol, and that, how many bits we transmit per second, and that is equal to the symbol rate times the number of bits we transmit per symbol, which happens to be the log 2 of m, where m is the number of possible amplitudes we use. Okay, so that was essentially pulse amplitude modulation in 2 minutes. And we will continue to work on this today to see how we can build a receiver for this and how we can evaluate the performance of that receiver. A common receiver looks something like this, where we still have pulse amplitude modulation to the left, and the transmitted signal goes over a channel which adds some noise to it, and this is the received signal. First thing we do is to filter the received signal with some impulse response, with a filter with the impulse response F, and then we get the output Y. This output Y, we sample that, and we take one sample every T seconds. So we have the same sample rate here as we have symbol rate. Or another way to say that, we take one sample here for every new symbol which is transmitted. And ideally what we would like to do is to have the output Y of k here, which is simply the amplitude of Y every T seconds. We would like that to be equal to AK. That would be good, because AK carries the information that we care about. So this is the, what should we say, goal. And this is possible to do, at least if we put the noise to 0. Okay, and if the noise is 0, we should really be able to do this, because noise is the only thing which is stopping us from transmitting information here. So in the noiseless case, we just form, we look at what the kth sample is, and then we see that we can write that as a desired term and an undesired term. And this undesired term we call intersymbol interference. This function h here is the convolution of the transmit pulse and the impulse response of the receiver. So we have some control over h here. We can design g and f together such that its convolution has the desired properties. I mean, that's our design choice. So what we typically would like to do is to make sure that h has this nice property that makes the symbol interference go away. And to do that, we pick h to be a Nyquist pulse. And what that simply means is that if we take t-spaced samples of h, we want all of those except one to be 0. So when n is equal to 0, we want this to be 1 ideally, because then our desired term would be ak, okay? Scaling factor 1. Actually, the scaling factor 1 here is not crucial. We can put that to anything we like. We can still, you know, simply divide yk with h of 0, and then we get ak. So h of 0 is not important. It's important that it's non-zero, but it's important that the other samples is actually equal to 0, because if the other samples, when n is not equal to 0, when the samples when n is not equal to 0 is equal to 0, then the intersymbol interference term disappears. Okay. So simply we would like to find a pulse h that has this property in time. And then I said, okay, this property can be translated into a requirement in frequency, where h here, capital H, is the Fourier transform of the impulse response h of t. And I just said that this could be easily done from the sample theorem. So let's just show that this is actually the case. So if you remember the sampling theorem, what it does, it relates the Fourier transform of the a continuous signal with its Fourier transform of its sampled version. So if we have a continuous signal xc of t that we sample every t seconds, we get a discrete version of the continuous signal xc, which is simply xc and t, like this. Okay, so we have a continuous signal xc, and we have a discrete signal xd. If I take the Fourier transform of xc, I get capital xc of f, which is just this integral from minus infinity to infinity, xc multiplied with complex exponential, and then integrated for time. Okay, so this is just a continuous time Fourier transform. Now there is a discrete time Fourier transform, capital XD, and then we need to choose a frequency variable here, and let's just pick a name capital F to not confuse it with small f here. And the Fourier transform of a discrete signal is not an integral, it's a sum from minus infinity to infinity, and then we have the signal xd of n times e to the j 2 pi capital Fn, like this. So that's the discrete time Fourier transform. The sampling theorem says that we can relate the Fourier transform of the continuous signal with the Fourier transform of the discrete time signal through a simple formula. And that formula is that xd of f is 1 over t sum from k from minus infinity to infinity of xc, the Fourier transform of the continuous signal, evaluated at capital F minus k over t, like this. So this is the sampling theorem. Okay, you've probably seen this before, perhaps not using this terminology, but anyways. Okay, so we know this. Now, for a Nyquist pulse, we have that h of nt. We know something about the samples here. We know that those are equal to n. It's equal to 1 when n is equal to 0, and 0 when n is not equal to 0. So what does that tell us about the Fourier transform of the samples? hd of f, which is this sum from minus infinity to infinity, and let's put in the samples here, h and t e to the negative j 2 pi capital Fn like this. Okay. So here's just the definition of the discrete time Fourier transform. So what is this equal to? Any suggestions? Pardon me?
If you convolute it back, or
No, it's very simple. We have this, and we just plug it in here. You don't have to do something in time or anything like it. You just plug in the numbers you have here.
is that the impulse?
This is an impulse, yeah, in a sense. A discrete time impulse. It's 1 when n is equal to 0 and 0 for all other n's. Right? And we just put that in here. So all of these terms will be 0 except one term when n is equal to 0. And when n is equal to 0, h and t is equal to 1. So what is this sum? Put in n equals 0 here, we get 1. Put in n equals 0 here, we get e to the raised to 1. Exactly. Oops, sorry. Up. 1. This is probably the easiest Fourier transform you ever done, right? Okay, so this is equal to 1. So it's not a function of f. Well, it is a function of f, but it's a constant function. It's equal to 1 for all f's. But we know also from the Fourier from the sampling theorem that this must be 1 over t sum from k minus infinity to infinity. And here we have the continuous Fourier transform of the signal that we have sampled. And this is the signal that we have sampled. So here we just have capital H, which is the Fourier transform of the continuous signal. And then we should plug in f here, and then k over t. And this is exactly what's standing here. Okay, so now we've proven that statement also. So if a Nyquist pulse, which is a discrete time impulse, okay, for any signal whose samples are like this, must have a Fourier transform which is like this. So which one we choose to work with, it depends on what is convenient. Okay, so regardless, so from this expression, the expression in frequency domain, we can draw some conclusions, and here are the important conclusions. That if G has a bandwidth of W, the transmit pulse has a bandwidth, is band limited, then we can say something when and when not it's possible to transmit without intersymbol interference. And essentially it's like this, that the best data rate, the best symbol rate we can hope for is 2 times the bandwidth. Then it's possible to do this, but it's only possible if G convolved with F is this sinc function. If the symbol rate is less than twice the bandwidth, then there are many choices of G and F that makes this work. And one such choice is that we choose H, which is the convolution of G and F, we call that H. So one such choice is to use what's called a raised cosine pulse. What it actually is a pulse with a raised cosine spectrum, which is this function here. And this will be a Nyquist pulse for all alphas which are in, we pick an alpha, so it's a design parameter. So we pick an alpha, and then it has this expression. The important thing of this is that it has a certain bandwidth here, which is controlled by alpha. So 1 plus alpha over 2t is the bandwidth of this, this signal. Okay, so we did that last time. Now, in many cases, okay, so before we go any further in this, there is an important thing which is known as spectral efficiency. So essentially what we would like to do is that we would like to transmit as many bits per second as possible. This is something that we would like to do. And we would like to do that without using the minimum amount of bandwidth. So suppose we transmit RB bits per second with pulse amplitude modulation, where the transmitted signal SOT has bandwidth W, then the spectral efficiency is, and we call that nu. That is the ratio between the data rate, RB, and W. So we would like the spectral efficiency. It measures how many bits per second we can transmit per hertz of bandwidth. Okay, so this is measured in bit per second per hertz. Okay, and typically we would like, what we would like to do is to have this as high as possible. We want to use our spectrum as efficient as possible. Now, if we use raised cosine pulses, then the bandwidth of the transmitted signal is 1 plus alpha over 2t. What can we say about the spectral efficiency? Well, first of all, we need to know what the data rate is. So what is the data rate? Well, it has to do with the number of symbols per second we transmit and the number of bits per symbol. So it's log 2 of m, that's the number of bits per symbol, and 1 over t is the number of symbols we transmit per second. Then the spectral efficiency, we simply get that by dividing these two things with each other. So it's the log 2 of m divided by t, that's our data rate, RB, and then we divide through with the bandwidth, which is 1 plus alpha over 2t, like this. And this is just 2 times the log 2 of m divided with 1 plus alpha. Okay. Now, so if we want the spectral efficiency, so hopefully this was clear. So if we want the spectral efficiency to be high, what can we do? Well, we have m and alpha here. So how should we choose alpha for the spectral efficiency to be high? Well, alpha is a number between 0 and 1. which alpha should we choose in order to maximize the spectral efficiency here? 0, exactly. It's not rocket science. So when alpha is equal to 0, we have nice spectral efficiency. When alpha is equal to 1, we only have half the spectral efficiency that we can achieve, right? So how should we choose M here for high spectral efficiency? Well, as large as possible, right? Okay, so right now it seems like we have no trouble in having any spectral efficiency we like, but just putting M to be a large enough number. But we will see later on that this is now limited. Actually, our choices of M will be limited by noise. So we cannot pick M arbitrarily large. Okay. Right. So now maybe you have been bothered by this, but what we have been talking about is the pulse H, which is the convolution of G and F. Okay. So we know what H we would like to have, but how are we going to split that between G and F? It's not so clear, right? We can do that in many, many different ways. Basically, if we take the Fourier transform of H, we get capital H. So we know what that would look like. And then we take the Fourier transform of G and Fourier transform F here. We get the product of two Fourier transforms since it's convolution. So basically, we would like to find a G and a G and a capital F such that the product is equal to this. Okay. Can be done in many ways. It turns out that the best way is to make G equal to F. Okay, so basically what we would like to do is to have the same G as F. Okay, so these are the same, this is the same pulse. This is equal to that pulse. Okay. And then we get into what's known as root raised cosine pulses. So very often okay, so very often we would like the f of t, and remember f of t, what is that? Well, it is the impulse response of the receiver filter. Okay. Very often we would like that to be related to G in a particular way, and why we want this will be clearer later today. So we want that to be the complex conjugate of G. Now we allow G for being complex pulse also. If G is a real valued pulse, of course the conjugation doesn't matter. And then we would like it to be a time reversed version of we put in negative t here. So basically we would like f to be G, complex conjugated, and then flipped in time. So it's time reversed like this. And if this is the case, then the Fourier transform of the left-hand side, capital F of f. So capital F here is the Fourier transform of small f. This little f here is the frequency variable, has nothing to do with the function f. It's just a stupid notation here. But this is the one that's used in the book. So, okay. So this is the Fourier transform of small f, which is then the Fourier transform of G star negative t. And it's not difficult to calculate what this is, but if you just trust me or look in your Fourier transform tables, you would see that this is equal to the Fourier transform of G. So the Fourier transform with G star, time reversed, is just the Fourier transform of G complex conjugated. Okay. So then the overall Fourier transform, H, so it's the Fourier transform of G convolved with F is then the Fourier transform of G. Small g becomes capital G, so this is the Fourier transform, and then multiply with the Fourier transform of small f, which we just realized is G star. So here we have G times G star f. Like this. Okay, and G star is a complex conjugate of G. Okay. Now, so if we get to this step in the derivation here, we see that we have a complex function multiplied with the complex conjugate of that function. So what is the result of this product? If you take a complex number and you multiply that with this complex conjugate, you get
The absolute value is squared.
exactly. So this would be then the absolute value of g over f squared. So it's a real valued function. No. Okay. So this is complex, but when we multiply them together, the real only the real part, okay, only all the imaginary parts disappears. Okay. So great. So now we have come to that conclusion here. To avoid ISI, we can choose GOT such that G of f magnitude squared is equal to a raised cosine spectrum, HRC f. Why is this? We know that the pulse HRC has this Fourier transform, and we know that this is a Nyquist pulse. Okay, so if we then can pick GOT such that its Fourier transform magnitude squared is equal to this HRC, then we know that we will not have any intersymbol interference. So to summarize what we have done, remember that we would like that the convolution of G and F, which we call H, should be a Nyquist pulse. Okay. One choice of this H would be a raised cosine pulse. The raised cosine pulse has this Fourier transform. Okay. Now, if we choose F to be related to G according to this equation, then after some calculations we got that H, the Fourier transform of H, is just the magnitude squared of the Fourier transform of G. Okay. So what we would like then is that this quantity, H, is such that we get a Nyquist pulse. One choice of capital H here is this, the raised cosine spectrum. So let's pick that, okay? So we choose G such that the Fourier transform of G magnitude squared is equal to this raised cosine spectrum. Another way to say this, if we just continue here, is that that G of f is the square root of the raised cosine spectrum. That will work. Right? Can we take the square root of this? Yes, no problem. It's a positive function, right? So it will not be complex. It doesn't matter if it's complex, but it will not be in this case. And then g of t, which is the inverse Fourier transform of the square root of the raised cosine spectrum, is called a root raised cosine pulse. Let's see, so I get the term in yeah. So G RRC of t. Okay. So what we have now is that, okay, so then basically we just take the Fourier raised cosine spectrum, we take the square root of that and inverse transform that. So I won't go through the motions of doing that, somebody else has done it for us, and then we get the following pulse in the time domain, like this. So this is the root raised cosine pulse in time, and this is the root raised cosine pulse in frequency. And the root here just comes because it's the square root of a raised cosine pulse in frequency. Any questions so far? Okay, so what we've done now is that we have designed G and F such that we don't have any intersymbol interference. We can make that, we can get rid of the intersymbol interference if we pick G as being a root raised cosine pulse. Where G is this. Okay. So what about F? Well, F of t should be then the receiver impulse response. It should be, according to our previous design that we started with, it should be G star and then time reversed. But if we look at this pulse here, it is symmetric. It's an even function, so I just want to sketch this a little bit. It will essentially be something that goes like this. Very rough. Okay. So it's even function. So when I time reverse it, I get the same thing. And it's also a real valued function. So this is just the same pulse as we started with. Okay. So this is actually a common choice in practice when we are interested in having intersymbol interference-free transmissions, that we pick the pulse to be a root raised cosine pulse, both at the transmitter side at the pulse choice we use, and also as the impulse response of the receiver filter. And if we do that, we will not have any intersymbol interference. Okay. So what is the problem with this pulse? Yes?
It's not causal.
It's not causal, that's one thing. It has something that on the negative side here, which is problematic. And furthermore, it also extends out to minus infinity to infinity. So it never goes down and becomes identically equal to 0. So in practice, we need to do two things. First of all, we need to truncate it, and then we need to shift it in order to make it causal if we do a real-time implementation of this. But that's engineering choices we have to do. But the theory tells us that if we allow for non-causal infinite length pulses, then we can get rid of intersymbol interference. In practice, we need to truncate, And we can truncate when the signal has decayed, when it's small enough, I would say. And then we just shift the whole thing to the right. And then we have a causal thing. And that's no problem, because if we shift it in time, the only thing we need to do is to shift the corresponding sampling times also with the same amount, and we still have intersymbol interference-free transmission. So those practical constraints are not a big problem to handle. Okay, but they need to be handled in a real implementation, of course. Okay, so if we then have, if we use these root raised cosine pulses, then the spectral efficiency is the same as we had before, as we did before. So it's the 2 times the log 2 of m divided by 1 plus alpha. Okay. Any questions? Okay, so let's continue then, and now before we actually go further into this, there a little bit of a review of certain things. Some of this is probably familiar to you. If it's not super difficult, but let's go through it, if nothing else, to get the terminology right. So we say that the energy or signal energy of a complex valued signal is simply the signal magnitude squared integrated for all times. Okay. And then we get a number, and this number we call the energy of that signal. The inner product. Have you seen these inner products before in the signal sense? Some of you have, yeah? So an inner product is like a scalar product between 2 vectors. So if we look at x and t, and these are signals, if we view them as vector, we can form something called an inner product or a scalar product. So with this, this notation with the angle brackets here, what is meant by this is this integral. Okay, so we take x, we take y, conjugate that, we multiply that together, integrate for all times, we get a complex number. Okay, and that complex number we denote by this. Okay, so we can think of this as a scalar product, if you like. The norm, a length of a signal, we already talked about that. It's denoted like this. It's x with double bars, okay, as opposed to x with single bars here. Single bars is magnitude, right? The absolute value if it's a real valued signal, or the magnitude of it if it's a complex signal. With double bars is the square root of x, the inner product of x with itself, which is the square root of this integral. So we put in x and x conjugate, multiply them together, we get x magnitude squared, and we know what this integral is. We previously said that that is equal to the energy. So the norm or length of a signal, it is equal to the square root of its energy. So if we think of energy as something that energy measures the size of a signal. Okay. A signal is of course something that varies in time, but if we want to summarize that with one number that indicates the size or length of that signal, it is the square root of its energy. Okay. Big energy, large size, low energy, small size. And if the energy is equal to 0, we have the 0 signal, and that is the smallest signal. Okay, now if we have this, we can then compute what the distance between 2 signals. And the distance between x and y, think of these as vectors. Well, it's only the length of the vector that goes from y and ends at x. Okay, so it's the length of the difference signal, which is then equal to this. Okay, and the distance between 2 signals, we will use that in our minimum distance receiver, right? So we want to compute the distance of the receipt signal, the distance from the receipt signal to all signal alternatives, and pick the best signal alternative, the one which is closest to the receipt signal. So any questions on these definitions? No? Okay. So then we continue. And continue our review. So the M-area minimum distance receiver, what is that? Well, the receiver knows the possible signal alternatives. We have M of those, and the received signal. And the first thing to do is to compute the distance between the received signal and the signal alternative L. And we do that for all L. Okay. So we compute this for L equals 1, 2, up to capital M. Okay. And then we choose the signal alternative index which has the smallest distance. So if we plot D of L like this, we find the minimum and then look at what is the index of that distance. So, and we call that M hat. Okay, and M hat is our decision on what has been transmitted. So basically, we guess that S M hat of T was transmitted. Okay. So minimum distance receiver, we get the receipt signal, compute all these distances, we pick the smallest distance and say, okay, I think the transmitted signal was the signal alternative that corresponds to the smallest distance. Questions about this? Okay. So this is a super important principle. This is what we want to do always. And it turns out that this is the best we can do in the sense that it will minimize our probability of making an error in our guess. And we will prove that a little bit later today. Okay, so let's continue now. Okay, so before we actually continue, so in this book, which it's where the pulse amplitude modulation theory is described, you have that in electronic form. If you go to Canvas, you can find this book at the library, and we use this chapter 531. So to be consistent with that, we changed the notation a little bit. So now H of T is now the transmit pulse. Okay, it used to be G before, but from now on we will call this H. We still have the F here, but very soon we will dispose of F and write that in terms of H also. So I'm sorry for this mix-up, but it's just to be consistent with the book, this is what we do from now on. Okay, so the transmit pulse is H, used to be G. For intersymbol interference free, we know that the convolution of H and F should be a scaled Nyquist pulse, and we have this. Okay, so we said that multiple times now. Okay, now actually what we want to do is that if we have a pulse, transmit pulse H, the best filter we can do under all circumstances when it comes to suppressing noise is to use a matched filter. Okay, so what is the matched filter to H? Well, it's a filter who has an impulse response F, which is this thing. Okay, and this thing is the complex conjugate of H and then time reversed. So very simply, if we have a pulse H that looks something like this, then the matched filter to this is a time reversed version of that. Okay. So this is F of T, H, time reversed like this. Okay, and complex conjugate is not visible here because this was a real valued function. Okay. So I think you've seen the matched filter in some previous courses also. But anyways, this is what it is. If we have a pulse H, we can find an impulse response which is equal to this, then this is a matched filter to this pulse. A matched filter then can be used to compute these inner products. So if the input is R and we have a matched filter, if the input is R and we have this filter, which is a matched filter to the pulse H, then we get an output Y, and then if we sample that at time 0, it turns out that Y, this sample, which is the value of Y of t when t is equal to 0, is the inner product of R and H. So let's prove that very quickly. So we have R as the input to a filter, and then we have an output which is Y, which we sample at time t equal to 0, and then we get a sample, a value Y, which is the signal's amplitude at time 0, like this. Right. Okay. And here we have an impulse response which is matched to the pulse H. Okay, so it's a time-reversed version of H with a complex conjugate to this. So what is Y of t? Well, let's just convolve R with the impulse response, F, where F is a matched filter. Okay. So the impulse response F is equal to this, which is then equal to the complex conjugate of H time reversed. Okay. So convolution is, by experience, I know that students, including myself, I thought convolution was this weird thing, right? It was difficult to get it right and so forth. But let me tell you this, convolution is our friend, right? And if it's not our friend, we need to become friends with the convolution. It should not be strange, right? To learn how to use convolution in an efficient manner is well invested time. Okay, so what we know about convolution is that it's an integral, and then it has to do with something with the convolution of R and F is an integral that involves R and F, and it should produce an output Y. So we have R, and then we have F, and then we need to integrate. Okay. So the first thing to do is to choose an integration variable, and we could choose any integration variable we like, as long as it's not equal to t. That would be a bad choice. Okay. So just pick your favorite letter, whatever it is, as long as it's not t, and choose that as our integration variable. I like U, okay? My favorite is U. Maybe your favorite is V, I don't know. You find to use V also, or W, or X, or Z, not T, right? And then the next step is to figure out what should be inside these two things. And here we have a little bit of freedom, but if you learn one way to do it, you can easily, by substitution of variable, get all the other forms. Okay. So for sure, there should be a U here, and there should be a U here, somehow. Okay. So I typically like to put U here. This is how I chose. And there should be a U here also, but there also needs to be a T somewhere. And why is that? Well, it's because the left-hand side here depends on T. So then the right-hand side better also depend on t, right? And, well, here's the thing. It should be a t here, and then it should be the subtraction of the integration variable. So if you don't know this by heart, go home and learn this, right? It's not so bad to learn this. And once you learn this, you should never fear convolution again. Okay. All right. So with that, a little bit of hyping up the beauty of convolution, let's continue with our problem here. So what do we have here? Well, okay. So this is the definition of convolution. But we're actually not interested in the whole thing. We just want to put in t equals to 0 because we would like to say something about y. Okay. So y of 0 is the convolution where we put in t equals 0. So this is just simply this integral again of r of u, and then we have f, and then instead of t we put in 0, and then we have then negative u like this, du. And now we're a little bit happy because here it says f minus u. Okay, and we know that f is equal to this. So that would be h conjugate now, since f of t is h conjugate negative t, f of u is h conjugate negative u, like this. I just changed from t to u, I'm allowed to do that. And then we changed the left-hand side, we changed u to negative u, and changed that to negative u in the right-hand side here. So f of negative u is just the h conjugate u. So what we have here is the integral from minus infinity to infinity of r of u, and then h conjugate u, du. Okay. Convolution, put in t equals 0. We see that the thing here, which the factor that depends on f, is f evaluated at negative u. And what is f evaluated at negative u? Well, it's just h conjugate of u. So just put that in here. Okay. And then we see that this, by definition, is the inner product of r and h. Take r, h conjugate, integrate for all time. T or u doesn't matter, same thing. And then we get this thing. Okay. Any questions on this? Okay. So with this matched filter, the key thing here is with matched filter we can compute inner products. And we know that inner products has something to do with distances, right? So we will use this property later on to figure out that, okay, the samples of the matched filter is somehow related to the distance between the input and the pulse to which it's matched. The impulse response. Okay, so a filter which is matched then to a time-limited pulse, okay, can also be made causal. Okay, and this is what we need for practical purposes. So by delaying the impulse response with a sufficiently long time, we can get a causal impulse response from a non-causal impulse response. So we basically just delay f with t0 seconds, and t0 you can pick what you want here. Could be 2 minutes or 2 seconds or millisecond, microsecond, whatnot. And then we get another impulse response here. So instead of okay, if we put in t0 equal to 0, we get back the matched filter. But we just delay this. And then if we have the input and causal filter here, we get the causal output. And if we then delay the sampling by the same amount by which we have delayed the impulse response here, we get the same output as we did in the non-causal case, right? So basically, if I delay the impulse response, I delay the output with the same delay. So instead of sampling at t equals 0, we sample at time t equals t0. And then we get the same output as above. Okay? So this is, there is no new theory here, it's just the practical way of doing things. So in your project, for instance, you would have to deal with causal filters. Okay. One thing we note from this also is that if R of t is equal to h of t, then the output, y of 0, what is that? Well, it's the inner product of R with H with itself. And we had a special name for this. Do you recall? The energy of H, right? Okay. Now, if I'm running late and you would like to have your break, you can give me small hints about this. So, I mean, we've done an hour now and the plan was 45 minutes. So, I'm sorry for that. I got carried away. But let's take a 15 minutes break here.